Hallo, liebe Zuhörende, hier sind wir wieder und schön, dass Sie auch wieder hier sind zur Neuauflage der Kosmos-Vorlesungsreihe aus dem Jahr 2019. Und mein Name ist Theresa Frommen, ich bin Postdoc am IRI-Thesis der Humboldt-Universität Berlin.
Ja, hallo, schön, dass Sie wieder da sind. Mein Name ist Christoph Schneider, ich bin Professor für Klimageographie am Geographischen Institut der Humboldt-Universität zu Berlin und freue mich, dass wir die Vorträge der Kosmos-Vorlesung 2019 uns nochmal gemeinsam anschauen.
Ja, und heute haben wir, nachdem wir jetzt schon einen Klimawissenschaftler hatten, eine Anthropologin und einen Literaturwissenschaftler, haben wir eine Pflanzengeographin und Makroökologin hier, und zwar Dr. Naia Morueta-Holme von der Universität Kopenhagen. Und sie redet mit uns über die Biodiversität und wie Humboldts Forschung auch die heutige Forschung noch beeinflusst.
Alexander von Humboldt war ja im Grunde einer der ersten Biodiversitätsforschenden und er hat auch als einer der ersten über etwas gesprochen, was wir heute Ökosystemdienstleistungen sprechen, also was die Natur mit ihrer Vielfalt und ihren Zusammenhängen eben an Möglichkeiten für den Menschen bietet und wie zwingend notwendig es auch ist, dass diese Ökosystemdienstleistungen erhalten bleiben. Also insofern war er ja einer der ersten Umweltschützenden. Und jetzt mit Professor Holm von der Universität Kopenhagen spricht jetzt jemand über Biodiversität, bringt das in unsere heutige Zeit, aber benutzt die Daten von Alexander von Humboldt, die der damals in Südamerika beim Aufstieg auf diesen Vulkan eben aufgenommen hat. Und es ist faszinierend zu sehen, dass man 200 Jahre später dieselben Daten nochmal benutzen kann, um dann auch zu sehen, wie die Änderungen, die der Mensch in die Welt gebracht hat, zum Beispiel jetzt durch Klimawandel, sich tatsächlich zeigt und dann man erkennen kann, wie bedeutsam es ist, dass solche Daten über lange Zeit gut archiviert und zugänglich sind und der Forschung erhalten bleiben. Ich finde das ein faszinierender Vortrag. Ich finde es aber auch faszinierend, so eine jüngere Forschende, der zuzuhören bei ihrer Begeisterung für dieses Thema. Ich wünsche Ihnen ganz viel Freude mit dem Vortrag.
It's a great honor to be here and have been invited and be able to commemorate Humboldt's 250th anniversary. And knowing that in this exact lecture hall, as well as in the Gorky Theater, he was giving his own lectures here in Berlin is it's really hard to describe because I've been working with Humboldt and thinking about him for quite a few years now. So I'm, as Christoph mentioned, I'm a microecologist or a plant geographer, biogeographer. All these terms cover the part of biology that looks at the big patterns in nature. You're probably all familiar with the fact that we have a lot more species in tropical areas than if we compare to a forest out here in Germany. But why is it that we have so many species there? Why is it that some species can only be found in very, very small areas? Actually, most species are like that, and some few ones can be found almost everywhere. If you have a garden, you probably think that nettles, for instance, they're way too abundant, and they're also very widespread. Yeah, so most of my work throughout my career has been based behind of a computer, and that's thanks to many of the big data sets that I've been able to work with for looking at this big patterns of especially plant geography. So today in this talk, I would like to introduce you a bit to the topic of this plant geography, which Alexander von Humboldt founded. I'm going to try to invite you on a small trip that's not behind the computer, but to the place where the field was actually born. And then I will go on to give you a bit of background on the history, what drove Humboldt to, what were the questions at the time, and then go through how the patterns of plant geography are, what the processes are for explaining these patterns, comparing the then and now, and then bring about some similarities. What are the ideas that are still valid today from Humboldt's time? What has changed? And in particular in terms of our changing environment today and the shift in focus of the field towards predicting what's going to happen in the future. And then finally, just a little bit about how his holistic view of nature might bring some inspiration for how we should solve global environmental challenges. So I hope you'll stay with me the next hour. I'm taking 3 steps, and I have to stop to breathe in the very thin air. What we hear here are the footsteps, my own footsteps, trying to climb very, very slowly up this mountain. I'm trying to focus on the footsteps of the guide ahead of me, and as I'm very slowly working my head. I'm the very last on the expedition right now, and I'm trying to ignore the very strong wind that's happening around me, and trying to ignore that on both sides of me, it's a really long fall. The darkness is helping. It's 4 o'clock in the morning, and we're trying to ascend to the very top of this mountain. It's really cold, and we are. It's really cold, and I'm trying to, but we really have to continue because we must find what we're doing right here is looking for plants. I'm looking for the very last plant that I can find on the side of this volcano. And every time I find a new one, the scientist in me should be really excited because then that means that the growth limit, overall growth limit of plants has shifted farther up. But really, because of my tiredness, I just sigh as they peek through the snow as they're teasing me. Then finally, at 5,185 meters, we find the very last plants, a Drabaretioides and a Pentacalia chimborazensis, the latter in full bloom in between the snow. We then try to fight our way to the 5,200 meters and call that the last point of the survey that we're doing here. The peak of the actual volcano is another 1,000 meters above us at 6,268 meters. And just like the person that we're trying to follow here, who was here 2 centuries ago, we must accept that there's no way that we're going to make it to the top. Now, he was really disappointed. I'm just relieved that we can go down back to safety. Because now our mission is done. We found the growth limit, and we can go back down. This is the volcano Chimborazo, which is the tallest volcano in Ecuador. And at the time that Humboldt was there, it was thought to be the tallest mountain on the Earth. Actually, the point, because of the placement on the equator, you are actually the closest to the sun. So depending on how you count it, it's still the tallest mountain on Earth. In 1802, we see here the father of biogeography, Alexander von Humboldt. And he documented the limits of plant growth. Now, our mission back then, this was in 2012, was to try to find out whether the distribution of plants that Humboldt found had shifted upwards or downwards, had changed at all. And I will come back to what we found then. But the mission of this talk is not only to give an answer of whether there have been changes to the distribution of plants, but broader whether our understanding of the whole plant geography has changed since Humboldt, and whether Alexander von Humboldt is still relevant to the field. So let's start with the definition of plant geography. Really, it's, like as I mentioned, is like usually the large patterns that we're looking at, and it's basically trying to answer the question, what grows where and why? And that's basically the question that is driving most of my research. Humboldt had a really nice definition of it that I like. He was very poetic in his writing, And he defined it as the science that concerns itself with plants in their local association with the various climates. And that this science that is vast as its object, which is the Earth, paints with a broad brush the immense space occupied by plants. So why would we want to know this? Why bother understanding and knowing what grows where? The very first one was the one that drove Alexander von Humboldt, is mere curiosity of trying to understand what is it that, how does the world work? What shapes the world around us? But the other more practical reason, nowadays especially, is that if we know where species are, and we know where the rarest species are, the most special ones maybe, the ones that are most important for the ecosystems to function, then if we know where they are, like here, and I'm making a map of where the hotspots of biodiversity are, then we know where to prioritize the protection of biodiversity, and thus meet the societal needs that depend on those ecosystems. So it's more of a, there's both the curiosity, but also the protection of biodiversity. Okay, so now I'm going to be talking about what are these patterns, and how are they seen back then and today. So let's travel a little bit back in time. The very first documentation, this is very loud. We're in the age of exploration, and naturalists are traveling around the world and finding all sorts of new creatures that they bring back home to Europe. Plants like this would be pressed, this is a Banksia from Australasia, would be pressed and brought back. And despite the fact that it looks all brown, you would need a bit of imagination to see how, and maybe some drawings to understand how it actually looked. But even dull things like this were incredible for Humboldt because they really sparked his imagination of how those parts of the world that he'd never seen looked like, and he really longed for going to see them with his own eyes. So it was these collections that would spark his curiosity. When his mother died, he inherited a big bag of money, and he has no doubt of how to use that. He spent it traveling for 5 years, leaving Europe and traveling to South and North America for a full 5 years. He would travel with the botanist Aimé Bonpland, which we see here at the foot of Chimborazo again. He's sitting here under the tent. And the two of them would collect, describe all the plants and animals, in particular plants, and then made all sorts of observation of the environment where these plants lived. Their observations formed the basis of this classic image that Humboldt created, which is showing the profile of Chimborazo. And the little wiggles that are here in the middle are actually the names of different plants and vegetation zones as he found them growing in different parts of the Andes. So these observations and all the descriptions and the whole work that Humboldt, his lifetime work, formed then the basis of the first global maps of plant distributions. So here we have what, as far as I know, is the very first global map. And it was a mostly unknown Danish botanist who put this together. All the observations from the Americas were mainly based on Humboldt's information. And then he also gathered it together with those of other travelers later. This limits the kingdoms of the world, where we see things like the moss kingdom. So it was fairly unknown at the time what really was growing in Siberian areas. And another fun one that was delimited was the Breadfruit Kingdom, because I guess that was the only thing that we knew about those islands in Oceania. As time went by and more collectors got information about what things grew, those maps became more detailed. We have here the one that was by Johnson and Humphrey, which shows, you can see how it becomes more detailed with the different vegetation zones again, and then also information on how these vegetation changed with elevation. Here comparing different mountain ranges from all over the world. So already in the 1800s, they were aware that there were a lot more species here in the tropics, and also that oftentimes a lot of species would have broad ranges in the temperate areas compared to the tropics, where a lot of rare species would exist. And it was going so well with these collections that in 1903, so 100 years after Humboldt visited Chimborazo, Schimper and his colleagues wrote that this delimitation of the floral districts was nearly completed, and that we were not far away from knowing where all species in the world were distributed. Then, once we knew all whether the species existed, a foundation will have been laid on which science can construct a larger edifice. And the reason I show this is because if we fast forward to today, it is true that now we can use these 200 years of collections and use the resources, the big databases and technological advances that have happened since the time of these explorations to gather together, put together all the knowledge that we have on the distribution of plants. So here is from an example, and several efforts, but this one is from the Botanical Information and Ecology Network, which I've been a part of. And here we see a map of the distribution of occurrences around the world. It's not only on plant observations, but we also have now a lot of information about the traits of these, what shapes do they have, how do they function, how can we link them to the functioning of ecosystems. And BN is just one among many other efforts to collect together the information on the distribution of life on Earth and understanding biodiversity. Now, we see here how over time here, per decade, this is just for BN, and the number of records have been increasing exponentially. But there's still some challenges that mean that we haven't really accomplished Schimper's vision and his colleagues' vision of knowing where everything grows. As you can see here, the blue areas is where we have records, but there are lots of areas, all the gray areas, we still don't know. And there are multiple reasons. Parts of them is just because of political reasons. The data is there, but we just don't have them for Russia, for instance, yet. But also still, many places are still unexplored. And who would have thought that in this time and age where we think that we know everything, yeah? And if we don't know where, and then also there are many challenges with the data, because a lot of these records might have errors in their georeferences or the naming of the records. There are strong biases in the sampling. As you can see, there are lots of records in North America and Europe. So there's still a lot of work to do. And as Humboldt also wrote, these botanical maps, we can only make them more exact in as much as we accumulate a greater number of good observations. And especially the good observations is what I take out from his quote. But nevertheless, despite all the challenges, we do have some updates on how we think the world looks like in terms of plant distributions. We can map species richness. Here we have the map, the newest map existing on the distribution of number of plants in the Americas. We see the strong spatial, the red areas being higher numbers of species and how they decline towards the pole. So confirming a lot of the general pattern, but getting a lot more detail into the quirks of it. We can also map where the rare and the common species are. This is some work that I did also during my PhD. And the blue areas are areas where small range species dominate in the region, whereas the warmer colors delineate areas that are dominated by this broad range species. Some more pretty maps that I can show is this one, for instance. So one of the big changes, it's not only about knowing where all of the species exist, but also we can just try to disentangle them regarding to their evolutionary history. And the theory of evolution was something that didn't come until after Humboldt's work. So this is this pattern would not have been something that Humboldt could have been looking for. And what I'm showing here is, what we see here is the change in the composition across space. So the red areas here, coinciding with the very high richness areas, and the Andes, the distribution of the mountain Andes, is where if you move from one place to another, then you're going to find a completely different community. Whereas in the lowlands of the Amazon, which we always think of super species rich, is actually very similar what you find in one spot and the next a kilometer away in the lowlands. But the pattern, this is like for all plants, but if we start looking at what about young species, well then it's very similar. Things that are evolutionary, emerged more recently in the history of life. But if you look at the old lineages, then it's completely flipped, where you have a much higher variation up in temperate areas. So these are kind of first steps in trying to then understand what drives speciation, what drives the emergence of new species and their migrations and so on. So now I got a little bit ahead of myself, because what is it that we need all these maps for? Why, once we have established the pattern, well then of course we want to know why they're like that. What are the processes that are driving them? And that's also what was driving Humboldt. He would be collecting fossils, plants, all sorts of measurements. But what he wrote was that, above all, I will observe the interactions of forces, the influences of the inanimate environment on plant and animal life. So already then, the stated purpose of plant geography and all of these collections was not just collecting per se and describing the patterns, but to try to understand what was driving them. So how could they infer the drivers back then? If we look at the tableau, the physique that Humboldt made, as I mentioned, we have the names of the species here, but what we see here on the sides are the measurements of the environment that he did. He measured all sorts of things. He measured anything that he thought could have an influence on the distribution of plants along elevation gradients. It was like the temperature, how much it rained, magnetic fields, the blueness of the sky, things that we would never even think today that made much sense. But by putting them all together by this in what is the world's first infographic, really, he could basically correlate these patterns. And from there, he derived that climate and a particular temperature was the one driver that was really important in delimiting. So it makes sense, yeah? There are some species that prefer cold, some that prefer warm. You don't think, if you think of a cactus, you don't think of it growing it out here in the middle of Berlin. It's not outside a greenhouse. So that was basically trying to put this together like this. What was unique about Humboldt was not so much that he saw that climate was important for the distribution of life. A lot of his contemporaries also described this. But what was really unique was that he didn't think this was the only force that was important. He thought of the world as a holistic thing where all things could interact with each other, and therefore it was important to try to measure of these different factors. If we go to today, then what are the processes that we think are important? Well, climate is definitely still regarded as one of the most important drivers of species distribution. This is reflected in that if we look at the distribution of the biomes of the Earth, where the rainforests are, where the Arctic tundra is, and we look at a graph where we distributed along the precipitation gradients and temperature gradients, you can see how they cluster together and separate, at least in this is a graphic representation, obviously. And a lot of and then some specific examples, we also have plants that are very clearly like don't tolerate frost, and that is very clearly reflected in their distribution. That's the case, for instance, for palms and for some cacti. But while a lot of the field since Humboldt was trying to figure out what was the one universal explanation for the distribution of life on Earth, we have had to go back a bit to what Humboldt was saying, that it's not just one thing determining it. So I'll now just go through some examples of other factors that are as important besides from climate. We have history, we have space, and we have interactions with other species, biotic interactions. So let's go back to the distribution of species richness here. One striking thing is that although we have this latitudinal gradient with higher richness in the tropics, if we compare the different tropical areas, we'll see big differences. So for instance, in what we call the neotropics in the Near World, have a lot more species of plants than, for instance, the Asian tropics and the African tropics. And here come in the roles of history that turn out to be very important. Now, just as a little background, well, I'll just go forward. So you're probably familiar with the fact that the plates that we're standing on once formed a whole continent, Pangaea, and then broke up into Laurasia and Gondwana, and those have been drifting around. This idea of tectonic plates and continental drift was something that was discovered or set as a theory much later than Humboldt. He and his peers saw things like when he found fossils on top of mountains, he thought those were mysteries that could never be solved. So even though he thought that history in terms of how climate might change could be important, then one major thing that has changed since his view of the world was that where he and his peers saw the world as something fairly static, today we know it's a lot more dynamic. So through geologic history, the continents have shifted, we have mountains that have been appearing, and all this has been impacting the distribution of species and speciation. So for the differences between the neotropics and, for instance, the African continent, in Africa we have, well, for one, the current climate, we have much more seasonal rainforests, or more unstable climate. But then in the past, we have imprints of past climate changes, and then this Andean uplift in the neotropics and other geological events mean that there has been a lot more speciation, a lot more new species appearing, a lot more migration, and less extinction in the neotropics. So as you can see, it starts getting a little bit more complicated than just saying that climate explains it all. Another place where we see the importance of history is through the effect of the quaternary climate changes. In the last 21,000 years, we've gone from having a huge ice sheet covering northern Europe to how it looks today. And if you look at species like many species such as the European silver fir that occur here in the black dots in southern Europe, if you compare the current distribution with what would be expected from the climates that they're living at, so their potential distribution, we see a big mismatch. It looks like there are areas that are much larger where it should be found. And this is basically that these species are not in equilibrium, have not migrated fast enough to track where the climate is suitable. And what naturalizations of the species where foresters go out and plant them, they reproduce just fine at the edges of these areas. So that supports this theory. It's not only in terms of species richness and the distribution of individual species, but we also see imprints of history, of changes over time in the distribution of rain size. So here again, we have the patterns of distribution of rare and common species, again with the more common widespread species in temperate areas and Amazon, and more rare species, especially in the Andes. And for this study that I published some years ago, we found out by comparing factors such as how seasonal is the climate in these different areas, how much has it changed since the last, so both in the short term, so do we have changes like here, we will have winter and spring and summer, or is it more stable like in the tropical areas? But then also like the stability over time in terms of the quaternary climate. So since the last ice age, where we had the ice age, you might be able to see it at the very outlines, the black outline up here. How does that compare? Is that more important than how much space the species have to spread out? And it turns out that what we find is a mixture of both. So the map here of the Americas on the left, your right, shows these 4 different colors, where the most extreme ones are the blue ones, which are dominated by the small range species, and the yellow ones are the ones dominated by the broad range species. And there are different stories across space. So there's a combination. Overall, we found that both the variation over time and how much land area there is to spread out was important for explaining the pattern. But if you dive then this distribution of where the dominant species are coincided with where the climate has been very unstable, both in short term in terms of seasonality and the long term in terms of the quaternary climate change. And on the other hand, we have the blue areas where the climate has been a lot more stable, and that has a small habitat area. So the story here to take from this is that we have here a place where conditions don't vary so much, but you don't have so much space. So that should give rise to, like, there shouldn't be so many extinctions, environment that is changing and making life difficult for species. But they can't really spread out because the habitats where they'll be suitable will only be found in very small areas. And on the contrary, on the other hand, we have an area here that has been changing a lot over time, which would select for good dispersers or very generalist species that can tolerate a very wide range of conditions. And interestingly, we also found that exactly where the limits go for this landmass coincide where these broad-ranged species existed. So again, here we see basically how there's this interaction between the effects of stability over time and stability over, or how much space there is, and how these explanations change across the continent. Now the third thing, now we talked about habitat, space, and then time. And the third example I want to mention, a third factor that is also turns out to be important, is species interactions. Now we know that there's some examples of specific species like the American chestnut that have been almost extirpated. The ranges contracted very much because of a disease. So that's a biotic interaction. But these interactions, which are usually thought to be important at the very local scales, can also have imprints in the macroecology and across many species. So what we see here is kind of a reconstruction of what the fauna looked like, the flora and fauna looked like in South America before the Panama, the North and South America grew together with the emergence of the Panama Land Bridge. What happened when when this bridge appeared geologically, it's obviously a very slow process. We had species coming in from the north that outcompeted many of these, and they went extinct. The extinction of these, as you can see, we have these like a giant ground sloth. We have also the giant armadillo. So these animals we don't see anymore, but they had a huge impact on the ecosystems, and it's something that we can still see today. And the way we see this is that many of these species would eat large fruits of plants. So there was this coevolution of the plants and the animals. When these go extinct, it means that there's nobody to spread those seeds. And today, if we look at the range sizes of species that have small seeds and large seeds, we see that the relationship, as we grow in size, it breaks off. So what this seems to tell us, and it's supported by some simulation work, is that these species with large ranges have been contracting in the distribution. So it's biotic interactions, but it is also, again, an effect of history, something that happened in the past. So just to sum up this section, we have that climate is a very important driver of the distributions, but it's not the universal explanation. We have a combination of many factors going on. So just like Humboldt said, in this great chain of causes and effects, no single fact can be considered in isolation. This is what the idea that everything is interconnected. Now, I've only talked about the natural processes driving distributions of species. And there is one thing I haven't talked about, and this is a new player. Maybe you can already guess. I could put a mirror here. It's all of you, all of us, all humans on Earth. We are so many people in the world today that our imprint can be seen from space. This is an image of the city lights that we emit if you were to see us from the moon. We have converted over half of the terrestrial areas of the world. And this has driven to some people like Earl Ellis, to some scientists, to say that these human processes, we really need to be looking at them in as much as all the natural processes. We can't just only focus on the natural ones anymore. We have what's we can call the Great Acceleration. Since the time of Humboldt, because of the Industrial Revolution, we've had a huge increase in the production, and with that, and of course also an increase in the wealth in the world, especially in our part of the world. But that has had such huge impacts. We see that, especially in the last few decades, that it's such a strong imprint in things like the carbon dioxide that we emit, the methane, of course the temperature following those, also the production of plastic. All of these things have been growing exponentially. And it has led some people to denominate this geologic epoch the Anthropocene. Now, we're all familiar with the fact that we humans are changing the climate. So it's not just, and what's different, I mean, we know from also what I was explaining before, that the climate has changed through quaternary history, and even way before that. and that species have been responding to that. And what's special about this time, though, is that we're doing it over the course of decades. So how is nature reacting to these changes? Plant geography, biogeography, if we're looking at other organisms other than plants, it's all the same method, can also give you some answers on how species are responding to global environmental change. The whole view of the world, because of climate change and all these human-caused global change effects, is, as I mentioned before, a lot more dynamic today than it was before. Now, if you have a species, and using something else than a plant, because they're cuter when they have big eyes, so changes is not a new thing. We've had these mass extinctions before, the plate tectonics have changed, and so on. But what is it that species can do? So either they can tolerate the changes that happen, they can adapt over time, they can move, they can migrate, or they can go extinct. Those are the 4 responses possible, basically, for species to environmental change. Now is the time where I want to go back to this founding place of the field of biogeography. Because when Humboldt was here and noted all this in his famous tableau, he not only gave us a new view of like the whole field of plant geography, the new foundation, but actually he gives us data, gives us observations of where these species are. And there are all sorts of problems with trying to use historical data to tell us something about how the world looked like at the time. But what we can do is go back and basically redo his study, go to Chimborazo, and see where these things are growing today, to give us some answers about, well, how, with the environmental changes that have been since Humboldt, has there been any change already? And we've seen this in other parts of the world, but the tropics are supposed to be a lot more stable. So we're really wondering what the results will be here. So as you already know, Timmy and I went back and struggling, had a very bad time on that mountain. But we did it. We went from 3,800 meters, and we would go collecting and identifying the plants, and up to the 5,200 meters, stopping every 100 meters up to delineate the distribution of plants. A lot more systematic than what Humboldt did, but at least ours is more repeatable. So after we collected, we spent some time in the plant museum, the herbarium, which helped us identify the plants, and that matching the names to those that Humboldt used at the time, which were not always the same, allowed us to then see what had happened on the mountain. So what did we find? Here we see the different species just named by a number, and how much the elevation had changed on the upper limit of them. All the green parts are ones where we found the individual taxon at a higher elevation than what Humboldt had reported. Now, it's biology, it's the world, it's not a hard sciences, so of course there are lots of exceptions as well. But overall, if we average it out, we have an upward shift that was over 500 meters in average, both at the species level and at the genus level. And this allowed us to make it sort of like an update of his tableau, where we can show how the distribution of the vegetation was 1802 and what it looked like in 2012. And overall, one of the big changes that happened is that, the vegetation has shifted, so not only the species, but all the vegetation zones as well. And the overall growth limit of plants has gone from the 4,600 meters around there that he reported, also over 500 meters, to 5,185. what the reasons behind this is, well, this is all consistent with the climate warming. The glaciers on the mountain have been documented to have receded very strongly. So there's both an opening of habitats that plants can colonize, but also the temperatures along the whole gradient that have been shifted up. So our findings are consistent with that. If we look at how it is out in the rest of the world, when people put this together, really the main response to this climate warming, well, for one, it has impacted all sorts of things on the life history of plants. The genetic diversity, the body size, also changes at the population level and at the community level, but the prevalent response are these shifts in the distribution. They're migrating, they're moving. Now, if they could just follow the climate, maybe it wouldn't be so bad, but we are living in a world that has been strongly converted by humans in other ways as well. So we have, and this migration is interacting with changes in the land use and with a lot of other factors that are stressing and making life pretty hard on many of these species. And usually when we talk land use changes, the impacts that we see are usually at the regional scale, but are we really seeing it also at the global scale, at the microecological scale, or is it only the climate changes that are global? Now, some of my colleagues did this pretty neat study where they looked at where are forests distributed today. And it turns out that most forests across the whole world are on the high slopes of mountains. Or even if you have a flat area, if there's a bit of slope, there's a higher chance you're going to find forest there. It makes sense. If you look at a valley, you have a human settlement, and then we're going to be trying to do agriculture everywhere where it's flat. So that signature of the land use is actually something we can see at the global scale. So it's definitely something we see not just locally, but globally. This redistribution of species is not just interesting per se as a curiosity. It's maybe for some worrying because of the value of nature itself. But it's actually already also been documented to have impacts on the human well-being across the world. This is a recent review from just, I guess, 2 years ago. I was on maternity leave, so I thought it was last year. But our lives are very interconnected with how ecosystems are working. So we see the impacts already. Overall, it's not just the distribution changes, but with all these stressors that we have, climate change, land use change, invasive species that we're spreading around, poaching, this means that we're maybe entering what we call a new mass extinction event. We've had 5 of those in the history of life on Earth, but none in the history of humans. So it'd be completely different, a new thing going on for us. Species are disappearing, thought to be disappearing 100 to 1,000 times faster than what you would expect just from the random extinction of species that always happens in the fossil record. So what's the future going to look like? And this is the very last section that I have. Oh, next to last. So it turns out because of this dynamic, all the dynamics that are happening in the world, we have never before this field of plant geography that Humboldt founded has been more relevant. Nowadays, though, instead of only focusing on what the patterns are and what the explanations are for the current patterns, there's a lot, the focus is shifting towards trying to understand what the future is going to look like. So in biogeography, we have tools where if we know the distribution, it's basically what Humboldt did, right? So we have the distribution of a species here, depicted in Mexico. We have information on the current environment. We can derive from that a model that picks out what are the main drivers of this. And then with that, we can predict what the potential distribution is in the present. Or if we have scenarios for the future, how the environment is going to change, we can then see how shifts are going to happen in the distribution of the species, what the expectation is anyway. This is the most simple correlative type of model that we have in the field. But of course, if we have information on how species are able to disperse, what they interact in other species, we can start putting all that information as well in more complex models that are maybe more accurate. So what the field gives us is that under different scenarios of societal change, under different scenarios of climate change, under different scenarios of land use change, we can combine this and see how the future is going to look like. And this can, of course, be used to help with conservation efforts. And if we're going to establish protected areas, maybe it's definitely relevant to know whether these hotspots of biodiversity across the globe are going to be in some of the same places or whether they're going to shift. But maybe you're wondering a little bit, well, this is nice, this is interesting, but what does it have to do with me? Now, just to, I would like to do a little question here. Of all of you, so now it's going to sound all completely off topic, but how many in the audience are rich? Do we have any rich people here? Can you raise, how many do not see themselves as being rich? Because maybe you're not daring to answer. Any hands? So not rich, not rich, not rich. Everybody else is rich or not rich? Or well, do you view yourself as a rich person? Are you wealthy? Are you a wealthy person? Some hands. Do you not see yourself as a wealthy person? Can you then raise your hand? Okay, we have one there, like, it's not Caesar. Well, how many of you would like to be richer? Maybe that's easier to answer. How many would like to be richer than you are today? So it's like you're completely against the statistics. Like everybody, the whole society is trying to grow, to make more economic output, to get a better life. And it's not only here. With all the elections that are going on, I very much doubt there's some few of you that don't want to be richer. Otherwise, we don't have the problems we have. But anyway, my point is that, so the average Dane earns about, just so you know that I don't making up the numbers, about 965,000 Danish krona. That's divided by 7.5 and you have it in euros. So over 100,000 euros. And if I can find my mouse. So this means that if you live in Denmark, so accounting for the standard of life, which of course, how expensive it is to live there, 2 adults and 2 children, you're in the richest 1.5% of the world's population. How many of you have a roof that you can sleep under? How many of you ate today? How many of you have clean water to give to your kids or education to give to your kids? A really large proportion of the world does not have that at all. There's always somebody who's richer, but we are about the 10 or 20, I mean, I'm not that rich. I'm not the average Dane. But still, running my own statistics, I was still among the 2% richest in the world. This is quite striking when you're thinking of, why couldn't I buy those other shoes the other day? I hope that I made my point that we're all rich in this area. And all the actions, all the consumption that we have in this part of the world has a huge imprint in the rest of the world. Just like, here's a map of all the land used that needed is exported for producing the imported and exported goods of our countries, and everything points to the Western world, in particular Europe. The land use imprint that we have every time that we buy a cutlet of pork is really big. So we are in a situation, we are the most privileged of the world. We also have the largest responsibility towards solving the global biodiversity crisis and climate change for that matter. Just like Humboldt said, everything is interconnected. So what can we do about it? Well, for one, we need this holistic approach that Humboldt was advocating in terms of how we see the world. We also need it for solving the challenges. We need to solve them not only at the highest level, where our world leaders need to make sure that things like solving the climate change challenges go against the goals of biodiversity conservation. When we are planting new plantations and calling that forest restoration, that's really not a sustainable solution. Now, how you can, of course, now 3 days from now, we have the elections like here in Germany. So that's one way as individuals that you can make a really big impact is giving a voice to biodiversity. Try to think that maybe, I think of that, maybe I won't say how you should vote, but where I live, kindergarten has, how many teachers there should be per kid is a really hot topic right now. I think my kids are doing great. They're a much better childhood than I had in the small daycare in Barcelona. So I know at least where I'm putting my vote. You can look at your consumption and see what changes you can make individually. If you haven't, I made once one of these questionnaires that I won't do right now because we're running out of time. But it was like, well, how many things have you changed after you learned about climate change as an individual? And there was very, very few hands. Now, of course, it does not matter what one person is doing, but if we're all answering that we're not doing anything, then that's where the problem lies. Plant geography is giving us a view of how these crises is only going to worsen in the future. But to make these good predictions, we also need really good data. So another place where you can contribute is helping fill in the gaps of knowledge. And nowadays, there are all sorts of efforts, like bio-blitzes, where you can go out and record observations of different organisms. Lots of what we call citizen science projects. When we evolve individuals from all sorts of parts of the society, and it's part of kind of democratizing, making putting democracy into the monitoring of our living world. You can help fill the gaps, or even with collected data, if you don't know how to identify, there are projects where you can help the collections that have been made, but they're sitting there and we have not digitized them yet because there's no time and money for that sort of work in herbaria. So there's like a project in the Paris Herbarium where you can go in and like read out the labels. So there are all sorts of very interesting projects like that. But most importantly, if you're interested in nature, and especially if you're not so interested in nature, is that you can use Humboldt, I think, as an inspiration to waking up that curiosity that we all were born with in trying to understand and see the little things of the world and the big patterns as well. Go out and see it. There are so many places out there that are still not destroyed by us and that are worth conserving. So if you're not convinced of that interconnectedness, you can go feel it by yourself. Anyway, with that, and apologies for the technical problems that I would just like to thank you all for your attention and I will take any questions you may have. Thank you.
Das war der Vortrag von Dr. Naia Morueta-Holme. Und mir persönlich hat ja der Schlussteil sehr gut gefallen, wo sie dann dahin geht, Biodiversität und Du, wo es dann sehr viel darum geht, wie man auch als persönlich und auch als Wissenschaftlerin tatsächlich auch aktiver werden sollte.
Das ist total wichtig auch für die Kosmos-Vorlesung, die ja genau wie das Alexander von Humboldt damals geframed hat, für, wie sagt man heute so schön, the general public, also für die allgemeine Öffentlichkeit gedacht sind. Und dann ist es auch wichtig, dass Wissenschaftlerinnen und Wissenschaftler auch mit ihrer persönlichen Message daraus gehen und sagen, hey, wir sehen diese Änderungen der Biodiversität und es ist notwendig, dass jede Einzelne sich einbringt, diese Biodiversität auf dem Planeten für uns und für zukünftige Generationen zu erhalten. Ja, toller Vortrag. Nächste Woche geht es weiter. Wir freuen uns wieder auf Sie für die Wiederauflage der Kosmos-Vorlesung und den nächsten Vortrag dann in einer Woche. Bis dahin, eine gute Zeit. Auf Wiedersehen.